When Canadians like you go to Wonderland and get on those roller coasters such as Leviathan, you will probably feel anxious, nervous, and exhilarated as you twist, turn, and drop during your ride. But what creates this sensation? How do these roller coasters work? Well, that's my job to help you understand the physics behind roller coasters. For most of the ride, roller coasters are moved by the gravitational potential energy and momentum. However, to build this momentum, the roller coaster needs to get to the top of the initial hill to create the fast and furious takeoff. Mechanical engineers use different methods to launch the roller coaster to the top of the initial hill. One of the most common launches is the chain lift. In these chain lift roller coaster rides, there are motors situated under the lift hill. As the motors turn, the chains looped around the motor move forward just like it does on a bicycle. The chain lift has a heavy piece of hook called a chain dog, which is attached onto the inside of the carts, and this causes the roller coaster to move forward along with the chain. There are also hooks called anti-roll back dogs that attach to the grooves of the track to keep the cart from descending the lift hill. And these anti-roll back dog chains are what makes the click-clack sounds as you move up the hill. At the peak of the lift, the chain is wrapped around a gear wheel, and basically the chain returns back towards the bottom of the lift hill, and the hooks will disengage while the roller coaster moves forward. As the roller coaster moves up the hill, it builds up potential energy. Another method that mechanical engineers use and is becoming widely popular is the linear-induced motors launch. The nerve-wracking anticipation time to get to the top of the roller coaster is reduced with this method, but it makes you slam into your seat at the start of the ride. The roller coaster accelerates from 0 to 60 miles per hour within just 3 to 4 seconds. Linear induction motors involves tiny motors called stators that are placed flatly along the track of the roller coasters. Stators are electrical coils wrapped around an iron core. A lot of the stators are placed along the launching pad, and some are placed as specific elements such as twists and turns. Another key component in this method are the conductors, which are highly conductive metals located inside the roller coaster. For each ride that uses the linear-induced motors launch, there's always nearby equipment that generates electric current and sends it through the stators. As the current flows through the stators, the magnetic field in the stators creates a secondary magnetic field in the conductor. It is a repulsion between these two electrical fields that propels the ride forward. As you can see, roller coasters have changed a lot over time. Did you know that the earliest recording of a roller coaster occurred in Russia during the 17th century? The first roller coaster was about 21 meters high and made of tall wooden structures with ice frozen over a long, sloping ramp. The riders had to climb a set of stairs to get to the launch area, where they would then climb aboard their sleds and slide down. Although the shapes of roller coasters have changed a lot with additions such as loops and banked curves, they all still rely on the law of conservation of energy. The law of conservation of energy states that energy is neither created nor destroyed. It can only change form. Over the course of a roller coaster ride, the energy that the roller coaster has at the top of the initial hill changes from potential energy to kinetic energy and vice versa at different points along the track. Potential energy is the energy that any object with mass has as a result of its position relative to the Earth's surface. The equation for potential energy is equal to the mass of the object times the height of the object times the acceleration due to gravity. As the roller coaster reaches the peak of the initial hill, it has the largest amount of potential energy at this point, since this is the highest height that the roller coaster ever gets to. As you can see, the roller coaster has no kinetic energy at this point. However, as the roller coaster moves downward, the potential energy decreases as a result of the drop in height. But since the total mechanical energy is the same at every point for a moving roller coaster, the change in potential energy is transformed into kinetic energy. Kinetic energy is the energy that any object with mass has as a result of its speed. The equation for kinetic energy is half of the mass times the speed squared. Mass is always constant, so if there's an increase in kinetic energy, that means there must be an increase in its speed. As you look at this animation, a little bit of the kinetic energy is changed back into potential energy as the roller coaster starts to incline at the bottom of the loop. At this point, the speed of the roller coaster slows down a little. At the top of the loop, almost all of its energy is transformed back into potential energy as the height increases. The speed of the roller coaster decreases, but the roller coaster still has some speed in order to continue moving through the loop. As the roller coaster returns back to the height of the ground after the loop, the roller coaster only has kinetic energy, which gives it enough momentum for it to go up the following hill. Changes in the energies can also be viewed as the roller coaster goes up the hill. The conversion of energy seems so perfect, however in reality it's not. Some of the energy that the roller coaster has at the beginning is lost due to friction between the tracks and the roller coaster and through other forces. Therefore, the height of the initial hill has to be the tallest, and the following hills have to always be shorter than the hill before it if the roller coaster is to successfully go over it. Remember, the total mechanical energy of the roller coaster at any given point is the sum of the energy lost due to friction and other forces plus the kinetic and gravitational energies. Now, let's take a closer look at loops. Have you ever realized that the roller coaster loops are in the shape of an inverted teardrop called a clothoid rather than a full circle? This is because it's safer to ride a clothoid loop than a circular loop. To explain this, you need to understand the centripetal force that occurs in a loop. When a roller coaster enters a loop, it undergoes centripetal force. Centripetal force is the force that pushes an object towards the center of the circular path. At the bottom of the loop, the force of normal exerted by the track on the roller coaster is pushing the roller coaster up. As you can see in this diagram, the normal force is always the appropriate size to combine with any other force to produce the required inward centripetal force. At the bottom of the loop, there is a greater amount of normal force acting on the roller coaster since there are no other forces acting towards the inside of the loop. But at the top of the loop, the centripetal force is the sum of gravity and normal forces acting downwards towards the center of the circle. The normal force is much smaller at this point. According to Newton's second law, force is equal to mass times acceleration. Therefore, centripetal force is equal to the mass times centripetal acceleration. But at the top of the loop, there's only force of gravity acting upon it in this scenario. So we can replace the centripetal force with force of gravity in this equation, which is equal to mass times gravity. On the right side of the equation, centripetal acceleration can be broken down into velocity squared divided by its radius. The masses are the same, so they can be cancelled out. Now, if you rearrange the equation to find velocity, velocity would equal to the square root of gravity times the radius. Now, for the circular loop, if you insert the radius into the equation, the speed will be 19.3 meters per second. And if you insert the clothoid loop radius, the speed will be 13.65 meters per second. As you can see, the circular loop requires more speed at the top of the loop to continue, which is dangerous for the riders. Back in the old days, when circular loops were used, they needed a greater amount of speed at the bottom of the loop. This is because as the height of the roller coaster increased, the speed of the roller coaster decreased. Therefore, when the speed of the roller coaster increased, the riders inside the roller coaster encountered high normal forces all throughout the ride, which caused whiplash and neck injuries. One famous roller coaster with a circular loop was the Flip Flap that opened in 1902. After a decade of its opening, the roller coaster was shut down due to the massive amount of riders that got injured. Nowadays, only clothoid loops are used for safety issues. Mechanical engineers use many basic foundations of physics to create a commercially successful roller coaster. They make sure that as a rider moves over the hills and loops, the forces acting upon the rider is constantly changing. But why does this make some riders feel as if they want to go on the roller coaster over and over again? Well, to understand these sensations, let's take a closer look at the basic forces acting on. Gravity is constantly pulling a person down, but nobody ever feels the force of gravity acting on them. They only feel the upward force of the surface, which is the normal force beneath them. Normal force is the force that gives the people the feeling of weight. But when an individual is in free fall, they don't feel the normal force. At this stage, a person feels weightless because the organs are weightless. The stomach is also weightless at this point, which is what causes the sinking feeling that people get while riding roller coasters. The same thing happens when you drive down a dip in the road. Without the feeling of normal force, the person on the roller coaster feels like they're plunging down toward the earth and will get scared. When anyone feels the danger of dying, their body releases adrenaline. A side effect of adrenaline is a rapid heartbeat, which most roller coaster riders have. Many people love roller coasters for the thrill that it brings. Here are some pictures of people on roller coasters.